Hello friends. So this will be the recorded video here. Initially I thought that I'll be editing the videos, but then actually it's a very long process and very time consuming actually, because I'm not very much comfortable with these softwares, and I have to learn basically all the software. So I dropped the idea. So this will be like a recorded video without any editing. So let's start. Yeah. So before we start, I hope you remember that we discussed in the previous class about the diffusion. And one point I would like to mention here is that, let's say if you remember this was a compartment having a high concentration of gas molecules moving randomly, and this one is having the low concentration of molecules moving randomly, but both were having the same temperature, as I mentioned in the previous class, the temperature Tt. And molecules were diffusing net from high concentration to low concentration. When they diffuse actually from high to low concentration, they just move here randomly. That means they don't undergo any change in their kinetic energy during their fusion or their overall energy. Anyway, in gas molecules there is no potential energy, so only kinetic energy. Also, you can say that the left compartment was at temperature T and the right compartment was at temperature T. And so when we mix both the gases, both are already at the same temperature, so they are in thermodynamic equilibrium. So why should there be a heat transfer from the high temperature to low temperature? Because they are having same temperature. So no heat transfer, and no heat transfer means no change in energies of both of them. That means both of these compartment gas molecules go ahead with their original kinetic energy. So during the diffusion, energy of the particles don't change, and this is what I have written over here also. And this is a very important thing that we need to keep in mind in today's class. Alright, so moving on. Yeah, so you may remember these bands, conduction band, valence band, and energy gap between them, which is called as Eg, which is the difference between the lower end of conduction band and the upper end of the valence band. So we know that Eg is equal to Ec minus Ev, and then there are others. So this is for the intrinsic semiconductor. Now you may also remember what happens for extrinsic semiconductors. So I have here the diagrams of the n-type and p-type. So this n-type, let's say, it adds a lot of donor impurities, isn't it? And in the previous class we discussed that these donor impurities, these have their last electron very close to the conduction band, because that is very loosely attached because of the factors that we discussed already. And so it requires a very less amount of energy, maybe roughly of the order of 0.05, to go from the from this donor impurity energy level to the conduction band. So not that much of energy. So electron is able to jump here. So as we can see in this n-type, there are lots and lots of electrons in this conduction band, as compared to the p-type, where you can see very few electrons which I have drawn. So each of this line, green line, is representing a filled quantum energy state. So lots and lots of filled energy states here in the conduction band, whereas in p-type the number of free electrons are very less. So very less quantum states are filled up. What about the acceptor energy level here of let's say a boron kind of trivalent impurity? Well, in this case the acceptor energy level is somewhere around very close to the valence band, and because of which this acceptor electrons, if they have to jump to the conduction band, then they require this huge energy gap. Again, we know that for silicon it is somewhere of the order of 1.1 electron volt. So that much energy is not readily available. So these electrons of this boron, you can see here, these cannot jump to the conduction band, and so these are tightly bound to the nucleus. But there is a vacancy which is created. So no electron can jump to the conduction band, so no extra generation of free electrons, but there is a generation of vacancy. So that's what's explaining the large number of holes in the p-type that we already discussed in the previous class. Now moving ahead with today's topic, today we are going to discuss diffusion in more detail. Now for that you have to understand what happens to these energy bands here in a p-n junction. So this is the energy levels for p-type, this is the energy levels for n-type, and now we are going to bring them close so as to form a p-n junction. Yeah. So normally we may accept this kind of a situation in which when we have joining p-type and n-type, actually we are not joining p-type and n-type separately. In fact, there is one single semiconductor only, and on one side we are putting p-type and on other side we are putting n-type. Yeah. So going ahead, so let's say this is a p-type, conduction band is here, n-type conduction band is there, valence band of p-type here, valence band of n-type, and lots of electrons in the valence band of the p-type, and lots of electrons in the conduction band of n-type. But this is not the actual picture. Why? Because when these two are brought together or they come in contact, we know that the diffusion happens, drift happens, and so that both of them balance each other in equilibrium. In the previous class we discussed that there is an electric field generation finally, and this electric field is from the positively charged donor ions to the negatively charged acceptor ions, if you remember this electric field. Now this electric field will actually alter the energies of electrons, and this is a very important concept to understand that diffusion under the forward bias condition, which is not very properly explained in your NCERT textbook. Some barrier height blah blah, some nonsense is given without any proper explanation. However, we will do a very nice explanation here. So let's consider the energies of electrons. So let's say we have a high potential point here, point A, and low potential point here, point B. Obviously the electric field will be from high potential to low potential. So at which point the electrons potential energy is higher, at point A or at point D? We know that any system in the universe will, when released from rest, actually will try to minimize its potential energy and move in such a way. For example, if we release a stone from some height, it wants to go down, and while going down it decreases its gravitational potential energy. Similarly, electron, if you release it from B, it will go towards this A. Why? Because electric field is towards right, so force is towards left. So along the direction of this force, it will move towards A. So A is the decreasing potential energy and B is the increasing potential energy. So this is a point of low potential energy for electron because it's a negatively charged, and this is a point of high potential energy for electron because it's a negatively charged. Just like a positive charge have got high potential energy at high potential points and low potential energy at low potential points, exactly opposite thing happens for the electrons. If you remember the formula, the change in potential energy of any charged particle is given as the charge into the change in potential. So if we want to go to higher potential energy, and this is a negative, and if we want this to be positive for going to higher potential energy, and charge is negative, so delta V should be negative. That means we should be going to lower potential. So lower potential is anyway, this is a very basic concept of electrostatics that you know very well, no need to explain it. Yeah. So moving on, so we can see that the electric field is there here from left to right. So along the electric field, the potential energy will increase now for the electrons. So this is high potential energy and this is low potential energy. And what about here? Well, in this case, in this side there is no electric field, and since there is no electric field region, in this region the energies are of one single values, and in this region the energies are one single values, but the energies gradually increase of electrons as it goes from this n side to this p side through the depletion region. Why? Because of the electric field. Okay, so this is how it is. So if you plot the EC level, this is all constant for these, but then along the depletion region this EC level increases, and then once it reaches the end of the depletion region on the p side, then again this E becomes constant, EC. So this is EC of n type and this is EC of p type. Similarly, this is EV of p type and this is EV of n type. And we know that the conduction band energies will be somewhere here. This is a conduction band. uh, so lots and lots of electrons, actually not many because this is a p-type, so very less electrons. But what about here?